Say the word tough. Say the word sheep.
Say the word bar. Say the word chair.
Say the word germ. Say the word back. Say the word base. Say the word bath.
Hi, this is Sinu Rathod. I have completed this project recently as a data scientist intern in a video development company. So I would like to discuss this project. Let's dive into it. First of all, I wrote here business understanding on our the problem and use cases of this project, and here the solution of the solution of this project using we are implementing this speech emotion recognition in many field or many domain to capture the the behavior or the emotion of the customer or any like the person we can say. Let's again what I'm doing is like here I mentioned the technical stack means what are the technology I used in this problem project, and let's go to the next next let's go to the main part of this project. First of all, what I did done over here is I imported all the required library for this project, pandas, numpy for the numerical calculation, and OS for the for to work with files. And here C1 for the visualization, advanced visualization, Matplotlib for the visualization, Libro, so we can able to work with the audio dataset, Libro, so display these both library used for use we can use for work with the audio dataset, and Python to display the audio, and want to if we want to play the audio, then we can use this library. Then from the SQL one hot importer, we are gonna be importing this library because our target variable or feature they contain that the value contain the categorical value in categorical value. So what we need to do is like we have to convert that categorical variable into the numericals. That is why we're gonna be importing that using this library. So lesson next is sequential library like model Kera sequential sequential library to stack the layers number of the dense layer and LSTM layer and dropout layer. Using the LSTM layer, we're gonna be building this model, and next we are using this dropout layer to avoid to tackle the overfitting problem. And here I'm importing some warning to avoid getting some the warnings. I'm using this I'm importing this warning libraries as well. So here I'm importing the dataset, entire dataset, which is the test dataset or Toronto dataset. That dataset contain already the label dataset with the different kind of the emotion of the different classes of the label. We can say from that dataset I'm extracting the path, and the label means and the path or path of that particular many numbers of the number of the audios are there. So all the audios path what I'm doing is I'm gonna be extracting or and placing the variable those audio path in this path variable, and here I'm extracting the labels. The labels or the target variable number of the target variable. Totally we have around 7 classes are there. So I'm putting the labels over in this labels variable, and next what I'm doing is like I'm printing the length of the path. Total number of the audios are is like 2800 audio available in this data set. So after that I'm printing the five some samples, the five sample parts of the path of the audio, and here I'm printing the labels of the audio. Okay, after that I'm creating and the data frame where I'm on creating the column called speech column, and there I'm putting all the parts, and here creating the label feature, and I'm putting all the labels in that particular column, and printing the top top five samples out of that. And next I'm visualizing means I'm checking the data set is whether labels labeled or not labeled. Like if the data set is imbalanced, then our model gonna be not perform well. So that is why I'm checking for to checking whether data set is balanced or data balanced or non-balanced unbalanced. So here the fear class contain 400 instances, and angry, disgust, and we can see all the classes contain on the equal records, or equal audios. So looking at this value, we can say that our data set is normally distributed, not normally, like equally distributed. We can say that data set is balanced data set. Here again, what I'm doing is, means I'm far to see the distributions, like the number of the records, number of the audio present in the in any particular class. I'm I'm writing this code, count plot for to check that distribution. Like angry class contain total 400 the audios, and fear class contain 400 audios as well. So we can, looking at this plot, we can say our data set is normally distributed. After that, we are plotting the wave plot and spectrogram to get the information about the video, like information about the our audio, or how our audio is like the loud audio is like. Next, here I'm writing the code to plot the wave plot. Wave plot means show the loudness of the audio over time, means over the time how our audio is like, the sound is gonna be like it's increasing or decreasing. We can, for to check the loudness of our the sound, we can use this wave plot. And next is spectrogram plot. We are going to be plotting the spectrogram plot as well. What it does means, spectrogram plot is visual representation. Spectrogram frequency sounds or other signal that vary with time. It can vary with the time. It's a representative frequency changing with the respect to the time given audio changing over the time, we can say. Like here is the function we are writing to print that spectrogram plot. And after that, we are printing one example, one audio over here. And you can see here, we plotted the wave plot, and here is the spectrogram plot, and here is the audio.
Say the word tough.
We can able to hear this
Say the
audio as
word
well.
tough.
Now let's here again I plotted the angry, like audio, like one instances on one. What I did is, like I'm printing one angry audio, like audio from the data set, and here is the wave plot, and again here is the spectrogram plot. We can say,
Say the word sheep.
this is, then just by listening to this audio, we can say this
Say the
audio
word
is
sheep.
angry. Emotion contain this audio is angry emotion. Let's here again I'm plotting the disgust. Let here the wave plot, and this is again a spectrogram plot. Let's,
Say the word bar.
I think this audio belongs to the disgust class. And let's again I'm plotting this natural the emotion. Now we can play this one.
Say the word chair.
Yes, it is natural. And here sad as well. Here we can see again wave plot and spectrogram plot. And this is,
Say the word germ.
yeah, this is sad. I would say, like we would say, this is sad class audio. Again here, I'm using the data augmentation technique to increase the diversity of the data set. And training, if our data contained more amount of, if to train our model, we need lots of data. Like how much of data our data, like in data set data is, then that much of the thing will learn from from the data. Our model will learn from the data. So we need, we must have large amount of the data set, and large number of the audio or data, we can say, to improve. In the Terento data set, we have already seen that, like there is 2,800 total audio. I think we need more number of the records, like more number of the audio to train our model, so that our model can perform, give the accurate result, means give the good accuracy, we can say. Like here the augmentation technique I'm gonna be using. And there are so many different kind of augmentation technique. We use like your time stretch. We can using the times and stretching the time, we can increase our audio, like we can duplicate our audio, we can say. And here I'm using the pitch shift technique also, we can able to use. And another one is like here injection, noise injection technique. And time shifting. There are so many zero out of empty indices. Okay, this is time shifting as well. So there are so many other techniques are also like maybe available on the available to increase the data and audio data. I haven't implemented. I just implemented these many. I just use these many techniques in my project. So okay, let's go to the another technique here. I'm using the future extraction technique. I'm last and ultimate goal is to is extract the future from that audio, and feeding that the future to our LSTM model. That is what our main goal is. Here I'm extracting. There are so many different kind of technique we want to be used, like commonly used for to extract the future from the audio. Here I already noted some techniques. I think here future extraction techniques. First of all, there are future chroma features, and spectral features, spectral centroid, spectral bandwidth, spectral flatness, and spectral sorry, like zero crossing rate. And yeah, and this is also root mean square and linear prediction coding. There are so many techniques, but when it comes to me, like I just use some few techniques only to extract the feature. Like I would say only one MFCC, male frequency cepstral coefficient technique, only used for to extract the feature from the audio. And here the features, like after extracting the feature, only I'm extracting 40 features, 40 features from the audio, and here printing those feature again from using data frame containing the speech, means the feature speech from column or feature contain the parts of those audio, and extracting the the feature from those audio. And here what I'm doing is we can extract the feature or the audio file. Okay, I'm extracting here just from one sample, like one audio. To extract the feature from the and all the audio, like in the data set, I'm using this code, like I'm applying writing this code. And here this is the augmented data, extracting the feature from the augmented data, and the extracting feature for the original data. And again after extracting, I'm printing the printing those the features, like augmented features. And again I'm printing those the features which is extracted from the original data set. And then I'm printing the shape of those, like on the features, like this is the augmented one, and the augmented shape and MMC. I think it's duplicate happened, no problem. We can say like 20,000 2,800 total augmented audios are there. And we are combining the augmented images and augmented audio on the original feature, email, the feature we extracted from our augmented and augmented audio, and the original audio. We are combining those both of those two. After combining this audio, we are going to be increasing our data sets, and by doing so. So here after combining converting combined feature into the numpy area. And like we know that, like in any particular any algorithm just accept it will accept only number, not directly audio. So to we are converting that, the entire all the features, like the feature we extracted, the feature we are converting that features into the 0 and 1 format, so that our algorithm get accept, and it will get trained. It will accept and train on this data set. We are going to be training that, giving that 0 and 1 in the form of 0 and 1 to our model, so that it can train. Or again here we are expanding the dimension, like extra dimension to make shape compatible, like our LSTM model accept these dimensions. So like we are expanding the dimension. Again here combining the original and augmented levels. Yeah, like definitely we augmented the independent variable, means like those the audio, but we haven't we should have to augment those labels as well. So we need here we here one hot encoding we are applying, because our data set is data set on the target variable, target or like label contain the categorical, it is a categorical problem, not categorical problem, but our label contain categorical value. So to convert that categorical into to number, we need to use this one hot encoder technique. So I'm using this one hot encoder, and after concatenating and converting this to numpy. numpy, and here I'm fitting on the transforming that one, applying this one not encoder on this combined combined label. And again I'm printing this y shape. This is the output that we got. It's like we have in our project, we're gonna be like we have total 7 levels, like angry, 7 classes, like that. Those are like angry, sad, disgust, and so on. There are some other emotions as well. And finally we are building the model. We done a lot of data pre-processing, and we done some EDA as well. And we use some technique to extract the feature from that the entire audio data, and those features we are feeding to our like we are converting those feature to 0 and 1 format. And again we are feeding that data to our LSTM model. Here we are creating and building the LSTM model. Here I'm importing the libraries here, Denson LSTM, and stack sequential LSTM model using the sequential approach. Here 256 like LSTM units I'm gonna be, the neurons I'm gonna be using, and the return sequence falls, return sequence falls, and the input set. This is our input set, and input shape of our image. We extracted total 40 features from our audio emirate. Like so, we are feeding that shape over here to the LSTM, and we are using this, the dense layer, or hidden layer, we can say. Here we are giving the 128 neurons, like using in this hidden layer, and activation function I'm going to be using like rainbow activation function. Again here we are using another layer, dense layer. We are using the total 64 neurons in it, and using the rainbow activation function. Again here I'm doing same thing, like dropout I'm using for to tackle the overfitting problem, dropout layer to prevent the fitting problem. And here again I'm using the dense layer. We are using dense layer and dropout as well. And finally we are giving our 7 classes to the dense layer. And this is, we can say, this is our output layer. And activation function, we're going to be using softmax activation function, to get the value in the form of probability. That is why we're going to be using softmax activation function. And here we are combining our model using the last categorical function. Okay, categorical cross entropy loss function we're going to be using, and optimizer to update the weights. We're going to be using this atom optimizer. And we are using the accuracy matrix we are going to be using. And then I'm printing the model summary. Here is our total one dense layer. There will be the total, these many dense layer, and total these many parameters, trainable parameters. And then finally, we are fitting model we are importing this callback, and Keras callback. From Keras callback, we are importing the model checkpoint and the early stopping. Okay, a model checkpoint saves model during the training whenever it's improved. When the model, when we are training the model, if the accuracy is going to be increasing, then only we're going to be saving our model. Means it helps us to helps us to save our model when only our, while training the model, when our accuracy going to be increasing, then only it will save our model. It will monitor the validation accuracy as well. Like if the validation accuracy keep idle, or keep constant, then our model will not further run. We gonna be not fit, or we cannot save that model once. Early stopping. Stopping, if the validation accuracy is increasing, then only running the model, else stop our tail. We're saying like that. And then I'm after writing this checkpoint and early, and finally we are fitting the model. Means we are training the model on this x and y, and the validation we are splitting our data into 20, I think 20% and 80% for the training, and 20% for the validation. So we are running for 50 box and batch size 64 validation step, and the callback, this callback and early stopping here we used. And then finally we trained our model, and we got this much of accuracy, validation accuracy, this much. And we are printing the history of the accuracy of this the training accuracy and the validation accuracy. We can see till until 30 maybe 28 epoch, we can see our model gonna be increasing the accuracy. And after maybe even the validation might not be increasing. That is why it's terminated over here only. It not gone further, till 50 epoch it is not running, because validation accuracy might not be increasing. It is not increasing, obviously. And this is the loss. Right. Okay, this is completed. This is all about my project. Let me I just deployed this project in the environment. I'm using the Streamlit, stream using the Streamlit, uh, using Streamlit technique. So I wanted to show that one as well. CMD. Okay, Streamlit run output by enter. Here we go. You can see the deployment is also working fine. Yeah, well, it's running well properly. I'm browsing the file and again selecting this audio, and we go. Oops, got it. We got output. Let me.
Say the word back.
This is the wave plot, as you can see. Undetected angry. Yeah, it's working. The model is we got the good accuracy as well. Again, we'll do one thing. We'll browse another one sample. This is the angry. Let me go happy. We'll select this one and open this file as well. Play.
Say the word bean.
Yeah, it's working here. We can say we detect the emotion in this audio, happy emotion. Okay. Yeah, this is my entire project. Uh, hmm, okay, thank you.